The universe we see, the shimmering stars, the swirling galaxies, the planets we call home, is just the surface. Beneath this familiar reality lies a cosmos far stranger and more profound than we ever imagined. It's a place governed by invisible forces, filled with objects that defy our understanding, and driven by a destiny that remains shrouded in shadow. Tonight, we journey into that shadow. We will chase the biggest open questions in modern science. The phantom scaffolding of dark matter, the relentless push of dark energy, the impossible physics of black holes, the enigmatic flashes of fast radio bursts, the echo of the universe's first breath, the lonely search for life beyond Earth, and the ultimate question of how it all might end. Welcome to Mysteries of the Universe. Our exploration begins now. Our first mystery begins with a simple observation. Galaxies are spinning too fast. Based on the stars and gas we can see, the outer stars should be flung off into the void, like children letting go of a merry-go-round. Yet, they hold on. Something unseen, a vast and invisible halo of mass, is supplying the extra gravity needed to bind them together. We call it dark matter. We can't see it, we can't touch it, but we can map its influence. We trace it in the stubborn rotation of galaxies and in the vast cosmic scaffolding it seems to weave between galactic clusters, a ghostly skeleton upon which the visible universe is built. It outweighs all the normal matter we know by more than 5 to 1. It is the true architect of cosmic structure, yet we still don't know what it is. Only that it's there. Everywhere. The most compelling evidence we have comes from a cosmic cataclysm, the Bullet Cluster. Here, two galaxy clusters have collided at immense speed. The hot gas from each cluster, which contains most of the normal matter, crashes together, slows down, and lags behind. But the gravity, which we can map by observing how it bends the light from background galaxies, tells a different story. The center of mass isn't with the gas. It's with the invisible matter that passed straight through the collision, like a ghost. This separation of matter and gravity is our smoking gun. Somewhere, a new particle, one that barely interacts with our world, must be responsible. In deep, underground laboratories, shielded from cosmic rays, and within the furious collisions of particle accelerators, scientists are listening for a whisper from the dark. So far, only silence. An intriguing, deafening silence. If dark matter is the universe's invisible skeleton, then dark energy is its phantom heartbeat, and it is even stranger. For most of the 20th century, we assumed the universe's expansion, which began with the Big Bang, must be slowing down, pulled back by the mutual gravity of everything within it. But in the late 1990s, observations of distant supernovae, exploding stars that act as cosmic lighthouses, revealed a shocking truth. The universe isn't just expanding, its expansion is accelerating. Some hidden repulsive pressure embedded in the very fabric of the vacuum is pushing space itself apart, faster and faster. Missions like the Euclid Space Telescope and the upcoming Nancy Grace Roman Space Telescope are now undertaking the monumental task of mapping the positions of billions of galaxies to chart this cosmic push with unprecedented precision. The nature of this dark energy will decide the ultimate fate of our universe. Is it a cosmological constant, an unchanging, intrinsic property of space itself, as Einstein once proposed? Or is it something dynamic, a field that evolves over time? The answer dictates our cosmic endgame. A constant energy density points to a slow, quiet fade into a heat death, where the universe becomes cold, dark, and empty. But if dark energy is growing stronger, it could lead to a big rip, a future where the repulsive force becomes so powerful, it tears apart galaxies, stars, planets, and eventually, the very atoms we're made of. For now, the data hints at a steady hand, but the tiniest deviation from that constant would rewrite the end of everything. From the grand scale of the cosmos, we turn to its most extreme objects, black holes. These are the universe's monsters, born from the collapse of massive stars or growing to supermassive scales, anchoring the very centers of galaxies like our own. For decades they were purely theoretical, points of infinite density where gravity is so strong, not even light can escape. But now, we can see their shadows. The Event Horizon Telescope, a global network of radio dishes acting as a single Earth-sized observatory, has captured breathtaking images of that glowing ring of superheated gas, the last orbit where light can precariously skirt the abyss before plunging into darkness. From these same regions, powerful jets of plasma can be launched across entire galaxies, powered by twisted magnetic fields and accelerated to near the speed of light. And still, so many fundamental questions remain. What happens to the information that falls inside? Physics tells us information can never be destroyed, yet a black hole seems to erase it from the universe. This is the famous information paradox. And how did supermassive black holes, millions or billions of times the mass of our sun, grow so enormous so quickly in the early universe? Our models of stellar collapse and gradual accretion struggle to explain their existence. The very edges of known physics, the boundary between general relativity and quantum mechanics, live right here, at the brink of the event horizon. Look closely at that shadow. The cosmos is telling us a riddle about the nature of gravity, space, and time itself. We have images, we have simulations, we have the gravitational waves from their collisions, but we're still piecing together the full story of gravity at its most extreme. Then there are the cosmic ghosts, fast radio bursts. These are incredibly powerful, millisecond-long blips of radio energy, arriving from scattered corners of the sky. They release as much energy in 1,000th of a second as our sun does in days. Some sources have been observed to repeat, flashing unpredictably, while many others are one-off events, never to be heard from again. The prime suspects are magnetars, a type of neutron star with magnetic fields a quadrillion times stronger than Earth's. Yet, the environments where these bursts originate vary wildly, suggesting there may be more than one way to create them. Each burst is a precious postcard from deep intergalactic space, its signal stretched and dispersed by the sparse matter it passed through on its journey, allowing us to weigh the universe. Around the world, new radio arrays and powerful single-dish telescopes are tuning in, listening intently. They are now catching these bursts in real time, allowing them to instantly pivot other telescopes to the source to search for an afterglow in visible light. By triangulating their positions and studying their properties, we are beginning to probe the tenuous plasma that fills the voids between galaxies. With each new detection, the picture sharpens. We're turning these fleeting, mysterious whispers into a powerful new cosmic probe, a tool for mapping the universe's unseen material. How did any of this, the galaxies, the stars, the mysteries, begin? Our leading theory, inflation, proposes a truly mind-boggling origin story. In the first fraction of a split second after the Big Bang, the universe underwent a period of furious, exponential expansion, growing from smaller than an atom to larger than a galaxy almost instantaneously. This incredible event would have ironed the universe flat and magnified tiny quantum fluctuations into the macroscopic ripples we still see imprinted on the cosmic microwave background, the faint afterglow of creation. Those primordial ripples were the seeds of all structure, the gravitational high points, where matter would later gather to form the first stars and galaxies. Inflation makes a testable prediction. That violent expansion should have shaken the fabric of space-time itself, creating a background of primordial gravitational waves. If we can detect this faint ancient tremor, perhaps by looking for a specific polarization pattern in the cosmic microwave background, we would have a direct fingerprint of the beginning, a snapshot of the universe, at just 10 to the minus 34 seconds old. Experiments on the ground and planned for space are listening for that echo of creation. Amidst all this cosmic grandeur, one mystery feels uniquely personal. Are we alone? The question of life beyond Earth may be the most human mystery of all. For the first time in history, we have the tools to begin answering it. With the James Webb Space Telescope, we are not just finding new worlds, we are reading the chemistry of their atmospheres. As a planet passes in front of its star, we can analyze the starlight that filters through its air, looking for biosignatures, the chemical fingerprints of life, like oxygen and methane existing together, or other subtle imbalances that hint at biology at work. We're also scanning the skies for technosignatures, evidence of advanced civilizations, such as artificial radio signals, powerful lasers used for communication or propulsion, or even the faint glow of city lights on a distant world. The search is a monumental challenge. The galaxy is vast, and we don't know what we're looking for or even if it's there. But the odds are no longer zero. The search is underway, and finally, we confront the end game. How does the story of the cosmos conclude? If dark energy remains a steady, constant force, the future is one of majestic isolation. Galaxies will accelerate away from each other until they slip beyond the cosmic horizon, their light never to reach us again. The stars within our own local group will burn out, leaving behind a cold, dark sea of black holes and dead stellar remnants, a universe slowly fading toward a final heat death. But if dark energy strengthens, the end will be violent. Space itself could tear apart in a big rip, shredding everything from galactic clusters to the fabric of reality. Or perhaps the story is not a line, but a circle. Maybe gravity will one day stage a comeback, pulling everything back together in a big crunch that could reset the clock and begin a new universe. For now, we live in the glorious middle chapters of this cosmic epic, a privileged moment where we are able to look back at the beginning, look forward to the potential ends, and measure, map, and imagine our place within it all, while the last page remains unwritten. Let's recap the journey. An invisible form of matter scaffolds the cosmos, while a hidden pressure accelerates its expansion. Gravity collapses stars into impossible horizons, while mysterious bursts of radio energy ping the darkness from across the void. The first flash of creation imprinted ripples that grew into everything we see. Other worlds, orbiting other suns, may breathe with life, and the ultimate destiny of it all hinges on a single number we are still desperately trying to chase down. These are not unsolvable riddles. The next decade of astronomy promises a revolution. New observatories like Euclid and Roman, gravitational wave detectors like LISA, bigger and smarter radio arrays, and sharper atomic clocks will peel back the layers of the dark. We stand on the cusp of discovery. Expect surprises. The universe, it seems, always rewards good questions. If you felt your own curiosity spark tonight, that is the engine of all discovery. Don't let it fade. Keep asking questions. Keep looking up at the night sky with wonder. Stay curious.